3 years ago, Marquette High School had the chance to host the 2006 Nobel Prize winner in physics, Dr. John Mather. He came and he talked to our high school physics and chemistry and math classes about his project that he was working on in launching a new telescope that was going to help us identify the age of the universe. One thing he said during that presentation has stuck with me for a very long time, which is there are as many numbers larger than 1 as there are numbers between 0 and 1. So if you think about that, if you're drawing a number line, if this is 0, this is 1, and this is -1, it's hard to imagine that the amount over here is the same as the amount over here. But if you take any number over 1 and you just add 1 to it, you could make it infinitely big on the bottom of the denominator, and that makes the number smaller and smaller, but it will never get less than 0. That concept is really important when we're talking about Keq. So Keq is how we measure the favorability of a reaction. So Keq is a ratio. Keq tells us if the Keq is greater than 1, that means that the reaction favors the products. If the Keq is less than 1, then the reaction will favor the reactants. Remember, when you're dealing with chemical equilibrium, this is not like most of the reactions we have done all year long. All year long, up until this point, we have said if a certain amount of reactant fully reacts with another reactant, it will produce a certain amount of product. Well, in this case, some of the reactant reacts with some of the reactant to produce some product, but that reaction will continue forming product, and that product will then reform into reactants. So this unit is a little bit different. To help understand what Keq is, we're going to use this sample equation. So at equilibrium, the Keq is the ratio of the products to the coefficient of their, or to the power of their coefficients, divided by the reactants to the power of their coefficients. So for a reaction like the one listed here, if you wanted to calculate the number of Keq, so Keq is the number, it's going to be greater than 1 or less than 1, you take the concentration at equilibrium to the power of its coefficient, and you multiply that times any other numbers in the products to the power of their coefficients. And so you will need to divide it by the reactants times the power of their coefficients. And together you would get what the Keq is equal to. To practice calculating 1 Keq, let's look at my favorite reaction. The Haber-Bosch equation is the reaction between nitrogen and hydrogen to produce ammonia. So in this example, you can see that this is a different kind of reaction than what we have used most of the year. So these two arrows, one going forwards and one going backwards, shows that some of the reactant really reacts with some of the product. And in the end, so at equilibrium, you would have some of each of the reactant and some of each of the products remaining at the end. So in this case, since we're dealing with equilibrium concentrations, we mentioned this little chart. We're talking about these ones. So at the end, it's already telling us that the reaction has ended. So in this case, we would have 0.15 molar here, 0.75 molar here, and 4.5 molar here. So, using the notes we just took from the slide before this, to calculate the Keq, you would need this expression. You have to take the products to the power of their coefficient divided by the reactants times the products of their coefficients. So what I mean by that is you have to balance the chemical reaction. So nitrogen, 1 mole of nitrogen will react with 3 moles of hydrogen to produce 2 moles of ammonia. So in order to do the Keq calculation, you have to take the final equilibrium concentration of ammonia and raise it to the second power. And then you have to divide it by the equilibrium concentration of nitrogen to the first power, because really this number is a 1. And then in the denominator still, you have to multiply it by the equilibrium concentration of hydrogen to the third power. So since these values are given in the problem above, all we need to do is plug in the numbers that are given and solve for the Keq. So in this case, 4.5 squared has to be divided by 0.15 times 0.75 cubed. So if you did these calculations on your calculator, 4.5 squared is 20.25, and 0.15 times 0.75 cubed will give you a small number, 0.063282125. And then all that's left to do is to divide the top by the bottom. So 20.25 divided by this long number in the denominator would give you a Keq equal to 320. So based on what we talked about for Keq, this number, Keq, is greater than 1. Therefore, favors the products. And look at the amounts of chemicals that are present. There are way more products than there are reactants. So if the number is very large, then you're going to end up with more product than you will reactant. It gets a little bit nuanced when you're looking at like the powers, like because you could have a large amount of one and a very tiny amount of another, but really, in general, you're going to always end up with more product if the Keq is greater than 1. Now that we know how to use concentrations to calculate Keq, we can also go the other direction. We can use the Keq to determine the concentrations. But this is where it's going to start. We are going to start using this ice chart. So last week we used this ice chart, and just last final reminder, I stands for initial, C stands for the amount that it changes by, and E stands for the amount at equilibrium. So this problem tells you that it has a Keq, so the Keq is given. And it tells you that initially you have 2 moles of hydrogen and iodine. So for both the hydrogen and iodine, you have 2.0 moles. This problem tells you you don't have any of the hydrogen iodide, so you have none of that. So if we were going to calculate the Keq, we know that the Keq has to equal whatever the concentration of the hydrogen iodine is at the end, squared, divided by the amount of hydrogen at the end, times the amount of iodine at the end. And so, since we don't really know those numbers, we're going to have to look at how much do they change by. So the Keq is 36, that's some number greater than 1. So we know that we're going to end with more products than we have reactants. But whatever that amount is, it has to be equal to this ratio. So the way we do problems like this is we look at how much do they change by. And since we don't know exactly how much they change by, we're going to use the molar ratios in the equation to help us make an assumption about the amount they change by is relative to the amounts in the molar ratio. So in this case, if you start with 2 moles of hydrogen, you're going to lose some amount of chemical. And because the coefficients of hydrogen and iodine are the same, iodine is also going to lose the same amount of chemical. Now, since hydrogen iodide is twice the molar ratio of hydrogen, or iodine, the amount that hydrogen iodide changes by is going to be twice the amount that iodine or hydrogen change by individually. So the reason that this is a 2 is because the coefficient in the reaction is a 2. So finally, at the end, at equilibrium, we can say 0 plus 2x is just 2x. And 2 minus x is 2 minus x in both cases. So now we are at a position where we have a number, Keq, is equal to 2x squared divided by 2.0 minus x times 2.0 minus x. If you wanted to write this a different way, you could say that 36 is equal to 2x squared over 2.0 minus x, and since it is multiplied the same, you could say that that is squared. So if you expanded this, if you made it like 4x squared minus 4 minus 4x plus x squared all equals 36, it starts to get a little bit more complicated. But if you are able to recognize that if you take the square root of both sides, this problem gets a lot easier. So take the square root of 36. I'll do it in a different color. So the square root of 36 is just 6. The square root of 2x squared is just 2x. And the square root of 2 minus x squared is just 2 minus x. So now we are in a position to use algebra to solve for x without having to use the quadratic equation or a crazy number of variables. So to simplify, we have 12 minus 6x is equal to 2x. So I skipped some steps there. If you need help, definitely let me know. But from here we have 12 is equal to 8x. And to get x by itself, x is equal to 1.5. So that's what x is. So if we take this number and go all the way back up to our equation, remember, hydrogen, the concentration of hydrogen is 2 minus x. So at equilibrium, hydrogen should have a concentration of half a mole. Iodine was the same, 2 minus x. It ends up with a concentration of half a mole. And so hydrogen iodide is supposed to be 2x. And so 2 times our x would give you a concentration of 3.0 mole. And if we're going to follow the rules for significant figures, this should have 2, 2, and 2, because that's what we started with. There it is. So we're going to pause here. There are other methods, but so far we have learned how to calculate Keq and how to use the squares method to solve for the change and equilibrium concentrations.